Okay, this lesson's a little heavy. As you can tell by the title, it says that we are going to be proving that a quadrilateral is a parallelogram. So essentially what we're going to do is take what we had with lesson 2 and we're going to flip that around. In lesson 2 we were told, given a parallelogram, we know that the opposite sides are congruent. We know that the opposite angles are congruent. We know that the diagonals bisect each other. There was a fourth theorem that isn't really relevant to today's conversation, but that if parallel lines are cutting off equal parts of a transversal, then it cuts off equal parts in every transversal. But those first three theorems, we're basically going to find that the converses are also true. Plus there's one additional theorem that we will work with. So today we're going to be working with a quadrilateral that has these characteristics, and we are going to show that if that is the case, if we have these characteristics, these properties, then that means that the quadrilateral is in fact and must be a parallelogram. All right? And so our goal is to determine whether or not a quadrilateral is a parallelogram. Here is the review from 6.2 that I just mentioned, and essentially we're going to flip all of these the opposite direction, having the converse of each of those theorems. All right? The first is the converse of the third one. So the third one, 6.1, 6.2, 6.3, given a parallelogram, the diagonals bisect each other. Here, if the diagonals bisect each other, then we know that that quadrilateral is a parallelogram. So the work here is a little bit interesting. The proof of this is actually not super challenging. But if the diagonals bisect each other, that means that this and this are congruent. This and this are congruent. That would be the definition of bisect. Then we can say that these angles are congruent by the vertical angles theorem, and these angles are congruent by the vertical angles theorem. Therefore, triangles 1 and 2 are congruent to each other by side angle side. Triangles 3 and 4 are congruent to each other by side angle side. All right? And if those pairs are congruent, 1 and 2 are congruent, 3 and 4 are congruent, then that means that their corresponding parts are congruent. All right? Now, if these two angles are congruent, then by the converse of the alternate interior angles theorem, these sides are parallel. Likewise, if these angles are congruent by CPCTC, then these sides are parallel by the converse of the alternate interior angles theorem. Therefore, given that the diagonals bisect each other, we know that we have opposite sides parallel. Therefore, this quadrilateral is a parallelogram. Please let me know if you'd like to see that written out as a 2-column proof. Or just play the video back and I told you all this, what the steps are. But if you want me to write that out as a 2-column proof, please let me know. Next, we have in theorem 6.6, if one pair, this one isn't tied to theorem 6.1 or 6.2 or 6.3, this is just another theorem. It's a very particular case. If one pair of sides in a quadrilateral is both congruent and parallel, then that quadrilateral is a parallelogram. This is a little bit interesting because we are given this information. We are given that this pair of sides is parallel and that that pair of sides is congruent. We do not know about the other sides. Now the interesting thing is that we might look at this and say, oh, we have a pair of parallel sides. That must mean that this is a trapezoid. Well, we have a pair of parallel sides that are also congruent. And in a trapezoid, the parallel sides cannot be congruent. All right, because if it were, then it would be a parallelogram. So here we have one pair of sides parallel and congruent. We did this proof, I think 3 or 4 different times back in Unit 4. Essentially, I will just draw this diagonal, which is congruent to itself, and I have the alternate interior angles are congruent. So these two triangles are congruent by side angle side. If these triangles are congruent by side angle side, then by CPCTC, I know that this angle is congruent to that angle. Right? The angle DAC is congruent to angle BCA. If those angles are congruent, then by the converse of the alternate interior angles theorem, I know that these sides are parallel. Now, both pairs of opposite sides are parallel. This is a parallelogram by the definition of parallelogram, saying that both pairs of opposite sides are parallel. Again, if you'd like to see this written out as a 2-column proof, we can do that. Or you can review the video and walk through each of those steps. Pair of sides, pair of alternate interior angles, reflexive side, CPCTC, converse of the alternate interior angles. Theorem 6.1 told us that in a parallelogram, the opposite sides are congruent. Here we're told that if both pairs of opposite sides are congruent, then our polygon is a parallelogram. So here we're given that these sides are congruent, that these sides are congruent. My proof is going to be essentially the same. I'll draw this diagonal, and I've got a reflexive side. So these triangles are congruent by side, side, side. Therefore, by CPCTC, these angles are congruent, meaning that these sides are parallel by the converse of the alternate interior angles theorem. By CPCTC, these angles are congruent, and then by the converse of the alternate interior angles theorem, these opposite sides are parallel, AB and DC. Therefore, this is a parallelogram. So what I'd like for you to write down is maybe work out the proof for theorem 6-7. Pause the video, include that in the notes. All right? That we have a pair of sides given, another pair of sides given, a reflexive pair of sides. Triangles congruent by side, side, side. These angles, DAC, BCA, are congruent by CPCTC. Therefore, these sides are parallel by the converse of the alternate interior angles theorem. These angles, BAC, DCA, are congruent by CPCTC. And therefore, these sides, AB and DC, are parallel by the converse of the alternate interior angles theorem. Please write that in your notes right now. Pause the video if needed. And then, of course, the converse of theorem 6-2. 6-2 said that in a parallelogram, the opposite angles are congruent. Here we'll say if the opposite angles are congruent, then it is a parallelogram. This one's going to be a little bit tricky because we're going to have to do this in a couple steps. So I won't have you write out this proof. But theorem 6-7 you should write out. Theorem 6-6 you should consider writing out. Theorem 6-5 you should consider writing out. This one, however, if I go ahead and tell you that this angle is congruent to this angle, and I tell you that this is reflexively congruent to itself, we need to somehow make the case that we are dealing with a parallelogram. So we somehow need to make this adjustment that we are dealing with both pairs of opposite angles congruent. Actually, we're not going to do it like that. I'm sorry. We're going to do it with both pairs of opposite angles are congruent. And therefore, we're going to show that what we are in fact dealing with is a pair of parallel sides by the converse of the same side interior angles theorem. All right? And the reason we're going to do that is if I know that these are congruent and these are congruent, that's the given. If both pairs of opposite angles are congruent, I'm going to call this x degrees, y degrees. This has to be xn and this has to be y. Now we know by the polygon angle sum theorem, we know that the sum of the measures of the angles in any quadrilateral is n minus 2 times 180, which in this case would equal 360. So I know that x and y and x and y are equal to 360 degrees, which means that 2 x's and 2 y's are equal to 360. That's just combining like terms. Now if I divide both sides by 2, I get x and y are equal to 180 degrees. All right? Now, if x and y, doesn't matter if it's this x and y, this x and y, this x and y, or that x and y, add up to 180 degrees, that means that they're supplementary. And if those angles are supplementary, then by the converse of the same side interior angles theorem, these sides are parallel, all right, if we're talking about this pair of x and y. Or if we're talking about this pair of x and y, then these sides are parallel by the converse of the same side interior angles theorem. All right, so that is all of the quick theorems and their quick proofs that I kind of worked out, not necessarily in 2 columns, but verbally there. I'd like for you to write out the proof of theorem 6-7 in your notes for the full credit today, and so make sure that that one gets in there. This one, if you don't write that one out, that's okay, but it's a quick algebraic proof. I'm a big fan of those. If you want to, again, this is a 2-column proof, I can write that out for you. But I thought that this would be helpful just to kind of get that information out to you. Now, I want us to kind of condense all of that information. In summary, and this is what's important here, in summary, we know these things to be true. All right, I want you to take a look at each one of those, read each of those. And then what I want for you to understand is that for theorems, 6, 1 and 6, 7, 6, 2 and 6, 8, 6, 3 and 6, 5, we can write those as biconditional statements. All right? And that's what these double arrows mean. All right? Diagonals bisect each other if and only if it's a parallelogram. Both pairs of opposite sides are congruent if and only if it's a parallelogram. Both pairs of opposite angles are congruent if and only if it's a parallelogram. All right? This one, obviously if it's a parallelogram, then the opposite sides are both congruent and parallel. But all that you need to prove that it's a parallelogram is one pair of sides that is both congruent and parallel. If that's the case, then we prove that with theorem 6.6. Okay? Understanding these as biconditional, biconditional, biconditional is, I think, important to kind of condensing that work or condensing that information into single statements instead of multiple statements. Now, the way that we apply this is going to look a little familiar because it's basically going to be what we had in the 6.1 lesson just flipped around. In the 6.2 lesson just flipped around. Instead of saying, given this parallelogram, find the value of x, it's going to say, find the value of x that makes this a parallelogram. Similar to what we did in lesson 3.1 and 3.2, when we learned about the alternate interior angles theorem and its converse, the same side interior angles theorem and its converse, the corresponding angles postulate and its converse. And so here, we're going to do something very similar with our examples. All right, so bear with me on this. In this situation here, we have some information. Find the values of A and B that will make this into a parallelogram. Well, the only way this is going to be a parallelogram is if this pair of sides is both congruent and parallel. So I have to show that these sides are congruent. The way that I'll show that they are congruent is by setting them equal to each other. I would have to say that 3b and 4 is equal to b plus 8. And then, in order to show that they're parallel, I'll have to show that these same side interior angles, or these consecutive angles in this case, are supplementary. So my other equation will be that a and a plus 30 add up to 180 degrees. We're able to create those equations based on the circumstance, and I'm going to be using theorem 6.6 that says a pair of sides, both congruent and parallel, will make this figure into a parallelogram. Obviously, doing the algebra here, I'm not concerned, and I'm sure you're not concerned with the step-by-step process there, but if that was a concern, there's the algebra. Sometimes we like to do this slightly differently. If you do your work using different steps, but you end up with the same answers as me, it doesn't matter what order we do those in, as long as we do all of our arithmetic along the way correctly. So those are the values for A and for B. It has to be both this and that in order for this to work. If A is 75, then 75 and 105 make 180, which means that these segments are parallel. If this is 10 and this is 10, then that makes these sides congruent, which means that these sides are both congruent now and parallel. Therefore, this is a parallelogram by theorem 6.5. Over here, I'm missing a key piece of information, and that is I need to know that these are congruent. So again, for theorem 6.5, it tells us that if the diagonals bisect each other, then we have a parallelogram. All right, and we went through the proof of that using side, angle, side, or side, angle, side, using the vertical angles theorem. Here, the way to make this into a parallelogram is if we know that PT and TR are congruent, and if we know that QT and TS are congruent. Well, QT and TS will be congruent if and only if 5x minus 8 is equal to x plus 8. And so to solve this equation, we'll subtract an x on both sides. We'll add an 8 on both sides. We'll divide by 4 on both sides. And we'll find out that if x equals 4, then we've got 20 minus 8 is 12. 4 plus 8 is 12. These are 12, both the same length, which means that they're congruent. These are congruent. Therefore, this is a parallelogram by theorem 6.5. So essentially, all that we're doing is taking those same steps that we would do in lesson 2, and we're just flipping them around and saying them backwards. All right? Here's a situation where we want to ask the question, is this a parallelogram? And the answer in this case is going to be no. Is going to be no, because we do not have the diagonals bisecting each other. I have that these are congruent and those are congruent, but that does not make this a parallelogram. We don't have the diagonals bisecting each other. If I have these congruent and these congruent, then yes, this is a parallelogram. I specifically drew this as a parallelogram, but then I marked it funky to mess with us, right? To make us stop and think, not just look by appearances, but to prove using logic. And here the diagonals do not bisect each other, therefore this cannot be a parallelogram. All right. I do hope that after you get to see all that information, as you pause the video, get down the notes, draw the pictures, organize the information, that as you're thinking about this stuff, that it's making clear that you are completely capable of proving whether or not the quadrilateral we are discussing or investigating is indeed a parallelogram. If you understand those properties of parallelograms and understand that they are reversible, then it makes our conversation around proving parallelograms, proving that quadrilaterals are parallelograms, a whole lot easier. Please let me know what questions, if any, you have.